So you see slides?
Yep.
Okay, yeah, I don't know. Seems like I don't use Zoom enough. Every time I use it, something's changed. Um, yeah, so tonight we're going to talk about pulsar scintillation, focusing on one particular pulsar, on some studies I've been doing with the 20-meter dish from Green Bank. And first of all, I'd like to acknowledge, um, I don't know how to get rid of that thing. I'd like to acknowledge the Pulsar Science Collaboratory at Green Bank, who operate this 20-meter. And within the Pulsar Science Collaboratories, the scintillation research team, and that's led by Jacob Turner and Juan Medina. And so I'm part of that team. The Pulsar Science Collaboratory is really designed to bring on board advanced high school students and especially college students that might be studying physics or astronomy or math and really want to learn more about pulsars. They have a training program set up, and then they integrate you into one of their research teams. And so I've been working with that. We access the 20-meter through the University of North Carolina Skynet, and then West Virginia University hosts the Nanograv Jupyter notebook server. So everything's done in Python there. And there's a couple of key reference papers here that were published last year that go into considerably more detail than I'll go tonight. And so the purpose here tonight is just a real quick introduction to pulsar scintillation. By observing that pulsars, the signals we get from pulsars, can be used as probes of the interstellar medium. The density variations in the ionized gas, mainly hydrogen, in the ISM cause these fluctuations. The fluctuations are what's the scintillation, where it arises in the radio signal intensity. And we can actually take measurements and learn about the size and density and distribution of the interstellar medium of the scattering structures. So these the photons from the pulsar, the radio photons, get scattered by various objects in between us and the pulsar, and we can learn some about those. And again, we're just focusing here on one pulsar from the Green Bank 20-meter. We've done presentations on pulsars in the past, and so some of what I talk tonight might be review and some won't be, but you're welcome to go look at the previous ones for some more background on pulsars. But pulsars are basically a highly magnetized, rapidly rotating neutron star. They're very exotic objects. It's the leftover crushed core from a supernova explosion. If the star started out with 10 to 25 solar masses, it'll end up as a neutron star. If it was more massive, it goes the final step down to a black hole. So neutron star is just one step away from a black hole. They're exotic. They have extreme chaotic magnetic fields that emit beams of electromagnetic radiation. And that's what we pick up as the radio waves. These neutron stars are strange, just being these tightly compacted neutrons only. And they speculate that they even have a solid crust of neutrons. And so they're still trying to learn what that crust looks like. In terms of scintillation, you can get hints of scintillation just by looking at the Presto plots like we look at here. The one on the left is our regular pulsar, B0329 plus 54, that we took at Haswell last June at L-band. It's a 25-minute collect, and on the left in the circle is the time phase plot with time at the bottom going up for 25 minutes. And you can see at the very bottom, there's really a barely detectable signal, and by the time you get to the end of it, it's a decent signal, and the whole overall plot is good. But that's an indication of scintillation, where the signal, the intensity of the pulse, is fading in and out over a period of minutes to hours. On the right is a pulsar from Green Bank, and it's 0355 plus 54. So these pulsars have the same declination, but different rate of session. So they're in the same general area of the sky, but they are completely distinct pulsars. Notice that the software, the Presto software used at Haswell is identical to the software that runs at Green Bank, and it makes comparisons easy. The Green Bank one on the right is 90 minutes, and so it's not as obvious, but you can see that the intensity of the phase of the pulse kind of fades in and out there. And over the years, we've seen several of the pulsars that we collect, we've seen scintillation in them. Scintillation is this slow variation. It can cover minutes to hours in the pulsar flux intensity, and it's caused by multipath interference through the interstellar medium. The resulting scintillation, which is just the intensity modulation, can be seen in dynamic spectra. So the dynamic spectra is, it plots the pulse intensity as a function of frequency and time. Well, that's what a waterfall is. So most of you are familiar with the waterfall for your SDR, where you're looking at the signal intensity as a function of frequency and time. The difference is you're looking at narrowband. Here, we're going to be looking at a broadband waterfall. And the enhanced regions of flux density are called scintilles. And on the upper left is an example of a dynamic spectrum, and the brighter regions are called scintilles. So on the left is frequency in megahertz. The Green Bank 20-meter telescope is not a research instrument, it's an educational instrument. It has, so it's 20 meters, it's a little bit bigger than ours. It has a very nice cooled front end on it, very nice cooled receiver, has 500 megahertz bandwidth. They got that really nice receiver as a hand-me-down. So when the Green Bank telescope, when the big one, when the 100-meter upgraded, then the 20-meter got this real nice receiver. So they have very nice front end. But something that we have in common with the 20-meter is the 20-meter does not calibrate the data, and neither do we. So when you're using a research instrument, then you take calibration measurements before, during, and after every observation so that you keep your instrument calibrated. So 20 meters is kind of like what we're doing. We're getting relative measurements. Nonetheless, we can get very good data and draw some strong conclusions. What we do is for 1 year, so that's one full trip around the sun, we take a 2-hour observation roughly every 2 weeks. And we're using the L band. The data there at Green Bank is generated into FITS filter bank, and that's a difference also. At Haswell, we use filter bank from our GNU radio, but it's in something called SIG-PROC format, which is just a binary file with a simple header. The FITS format is considerably more complex, and so that's something we'll have to think about is in order for us to do this. And so one reason I'm doing this is I'd like to be able to do it at Haswell, and we'll talk a little bit more about that. But once we collect the data, we perform the folding just like we do at Haswell, and we remove RFI. Then we form the dynamic spectrum, which I said is just a wideband waterfall, and that's on the upper left. Then you take that dynamic spectra and you basically slide a copy of itself over the top until it matches, and you get the two-dimensional autocorrelation function. And that's the second one from the top with the bright blob in the middle. Then what you do with the autocorrelation function is at time lag 0 and frequency lag 0, you take a slice. You take a frequency slice and a time slice, and you form these one-dimensional autocorrelation functions, one in frequency and then the bottom one in time. For the second one from the bottom, which is frequency, you can measure the scintillation bandwidth, which is defined to be the half-width, half-max of the frequency ACF there. And so once you fit a curve of the data, then you can get these parameters. And then the last one is the scintillation timescale, which is defined as the half-width at 1/E on the time autocorrelation function. So that's how we start measuring some parameters. We basically compute the ACF and fit curves, and then just get the measurements. So a second path that we do, so again, starting on the upper left with the same dynamic spectrum, is we're going to measure the scintillation arc. And so from that same dynamic spectrum, we make what's called the secondary spectra, which is basically taking the two-dimensional FFT of the dynamic spectra. It's called secondary spectra because we've taken the fast Fourier transform twice. So this second time is what produces the arc on a pulsar that is scintillating. So if the pulsar is not scintillating, you will not see this this arc that we have there in the middle. And so once you get that arc, then again, it's just fitting a curve. In this case, it's a parabola. You can run curve fitting algorithms on it to fit the curve, and then you measure the width, the curvature. That curvature then implies a distance of a thin screen model along the line of sight. And that thin screen model dominates the pulsar scattering and accounts for it. And often you'll see that these arcs are asymmetric. That can be due to interference and the scattering or refraction, but it's also just due to the Earth's rotation around the sun. This is a thin screen model taken right from the Handbook of Pulsar Astronomy. On the left is the pulsar with its velocity. It's moving in some direction. On the far right is the Earth with its velocity. And in the middle, you have the turbulent interstellar medium, which distorts and diffracts and interferes with the radio wave coming from the pulsar. Now, that can be modeled by one or more thin screen models, and it accounts for what we observe. So the thin screen model is not necessarily real, but it does account for what we really see. The scattering in reality is due to supernova remnant shells, that they have a very hot gas that affects the radio wave, also the ionized gas clouds, and just the turbulent kind of a patchy plasma. So the interstellar space is not quiet. It's very chaotic. Now, for this particular pulsar, here's the parameters, I guess, of interest here. The distance is just a little over 1 kiloparsec, 3,200 some light years is how far away it is. It's in the direction from us over by the Perseus arm. So in this map here, this image of the Milky Way, the sun is located there. It's actually at 0, 0 on the scale, but then this particular pulsar is at 358 right ascension and 54 declination. So it's over there to the left of it near the Perseus arm. And it's just, like I said, a little over 1 kiloparsec in distance. And it has a period of 156 milliseconds. We have detected this one at Haswell. It's got a 1400 flux of 23 millijanskis. So it's right at the edge of what we can detect, but we have detected this one. It took it 3 hours to detect it, but I don't know that we'd be able to do scintillation studies on it, but we would want to choose brighter ones. So just some examples now. This is from Green Bank. And the first thing you notice on the left is that data looks terrible. Yeah, you think it's Green Bank, it's in a radio quiet zone. They have some very severe noise issues there. And so right there at about 2,600 seconds, you see that big jolt of RFI. It knocked down the signal to noise. So this should always be steadily increasing for signal to noise ratio. Knocked it down to 0 and you start over. But what we can do, we have tools to remove the RFI. So we remove this, preserve the phase, and then we get this and say, oh yeah, it looks like a good strong pulse. And so we go ahead and proceed with the code, and we produce the dynamic spectrum, the autocorrelation function, and we get the secondary spectrum. And sure enough, it's got an arc there, and it's kind of asymmetric. And then we fit it. Now, It kind of depends on your eyes and I guess my screen, but that if there is a red line there, but it's hard, at least hard for me to see. Um, but that's what we do for each one. We take measurements and we do it over the course of a year. What we'd like to do at Haswell is do it for 6 months. 6 months would be 2 AU. It'd be halfway around our full orbit. So it'd be from one side to the other. It'd cover a good distance, and we could put up to 1,400 feed after the last EME contest, and then leave it up for about 6 months, and every 2 weeks have a team down there just to collect the data, and then we'd post process it. And I think there's 2 pulsars that we could do that way. Here's the next one. So this one looked a little bit better, but I trimmed off the end. So this is 5,000 seconds. It's 2-hour collection. Actually had 7,200 seconds. I just trimmed off the last part because of RFI. Got a very good strong response here. And again, here's the scintils in the dynamic spectra looking very nice and bright. Very good center ellipse there for the autocorrelation function. And then here's the secondary spectrum with the fitted curve that's kind of hard to see. But this just shows kind of arc evolution. The top 3 are, I'm calling it data 13, 14, and 15. So these are each 2 weeks apart, just showing how it changes over time. The bottom 3 are 18, 19, and 20. Again, these are roughly 2 weeks apart, just showing here it was kind of dominated on the left, just kind of in the middle, and now it's dominated on the right. So there's significant changes as we move, as the pulsar moves, and as the clouds of gas move around. Now, what we do is accumulate the data. So I've collected 24 sets of data. I discarded several because they did not converge, too much noise. And here's some measurements, just plotting the data that we measured, the bandwidth, the time delay, and the time scale. So the bandwidth is in megahertz. It's averaging around 5 megahertz of bandwidth. And the time scale is in minutes, and it's averaging around 3 to 5 minutes. There's going to be a significant variation in the individual observations in the parameters of individually because there's the dynamic spectra is different, and the pulsar is acting differently. What does not change is our screen distance. If we're postulating a screen distance, it should stay relatively constant even as these other parameters move around. And for this particular pulsar, there's not very much in the literature. What little I can find are reporting a dominant screen at roughly 1/10 of a kiloparsec, which would be 100 parsecs. And that's the same thing that I find. So I'm actually calculating screen distance 2 different ways, either a Gaussian or Lorentzian fit. Gets a 1/10 of a kiloparsec, and then we're also taking the arc curvature, and it's a little bit less than that. Now, along the line of sight from us to the pulsar at 1 kiloparsec is the local bubble and a supernova remnant. And so I'm not saying that it's the local bubble and this supernova remnant causing it, but that's a likely conclusion. We don't have proof of that yet, but it's likely. The models say, oh, at about 1/10 of a kiloparsec, you should have a dominant screen. And we look and say, oh, that's where the edge of the local bubble is and a supernova remnant. And you might ask, well, how in the world do I know that? Well, that's because it's been mapped out. Stella Ocker is an astronomer, and she has developed this 3D interactive visualization of pulsars that's put up on GitHub. Anybody can go get it. The sun is right here. This greenish blob is the local bubble, and each one of these is a different pulsar. There's about a dozen pulsars here. The blue line goes to the pulsar that we're interested in, 0355 plus 54 out here at 1 kiloparsec. So this is the blue pulsar, and I mean the pulsar we're looking at way out here, but it comes in and passes through the local bubble, and there's also a supernova remnant there. These other little clouds are molecular clouds and various hydrogen regions. So that's how we can say something like, well, at 1 kiloparsec, you got the edge of the local bubble, which might be causing the scintillation. Are there any questions?
Is it easy to get that information from Green Bank? You working directly with them?
Yes. So I joined the Pulsar Science Collaboratory,
Okay,
and you do everything there at their site. I don't actually, well, I could download the data if I wanted to, but everything's done there on their site. So it's all done remotely. The
okay.
data collection is done remotely, and all the data processing is done remotely on these Python notebooks. But they kind of help, they kind of train you and walk you through it. One reason they're doing this is big telescopes rarely will give 2 hours to a single pulsar. They might take a observation on a particular pulsar maybe for 300 seconds once a month. But that's not enough if you're doing scintillation studies, because to see the scintillation, you need about a 2 hour data collection. And so that's where we're thinking, well, we can actually offer this as a service, not only for DSES members, but also the community, where we are actually collecting useful scientific data on scintillation on these pulsars.
So there we'd be at a point sometime in the future, we could do a 2 hours, collaborate with them and compare at the same time what they're doing and what we're doing. A collection of data.
Yeah, we could do that. The difference would be just in the instrumentation. So that would not be interferometer. That'd just be two separate instruments taken at the same time. The difference would be they have a better front end than we do.
Yeah. Okay.
So Dan, would you be able to upload your data to their site then?
So that's something. So Ray and I just started kicking this around. I could, or I would download the software pipeline. So I would just I had asked Jacob for permission to download the data, download the software. It's a pretty extensive software pipeline, but I think we could reproduce it here. I would instead of generating data in our fill format, I would want to generate the data in the FITS format and then just use their pipeline. But if for some reason we didn't get rights to use their pipeline, then yeah, they would be happy to let us upload our data to there and run it there, because they're just trying to get more people, especially more schools. I did a little presentation on this to the Eads High School, but there wasn't anybody that was really interested in doing this. I think it takes a special kind of student that wants to jump into this.
Are there software tools that do the conversion between the two different formats?
They don't do it very well, because I've tried in the past to convert our fill format to FITS, and it messes up the header, and then you still have to go in and work, edit the header by hand, and it's like, oh, this is not a very good process. It'd be better. So AstroPy is the big Python library, and AstroPy has FITS routines. So it'd just be a matter of using AstroPy to generate a FITS from the beginning.
Okay. Because I think I think I've played around with the FITS file formats and the headers and things, but it may not be the same FITS, but
It's been around for quite a while. FITS has been around. This is actually Pulsar FITS, and of course, Green Bank has modified the standard format. They have a custom format, but it's just, they change a few columns. But FITS has been around for a while. There's still CFITS.io, which everybody uses, and then there's Python wrappers on it.
okay. Well, it might be an interesting software project for somebody.
Yeah.
Yeah, you'll have to tell me more about it sometime.
Okay.
All right. Thanks, Dan. Any other questions? We'll move right along this. Appreciate this. This is the presentation Dan was working on. And last time we had a meeting, he was under the weather. So we delayed it till this meeting here. So thanks, Dan. That's
Yeah.
great work you're doing with the Green Bank folks. So next on the list is the agenda is the noise figure versus noise temperature that Ray A0L will present. I'll let Dan check out of the
Do I still have that?
share window. There we go. And Ray, you're up.
Better turn on my microphone. Okay, very good. Let's share screen thing, I think.
Yep, hit the share green button.
And then I don't remember exactly. Oh, you see that at all?
No, you got to hit the share. The share did not work.
Okay. Get back.
Try the share again.
Oh, probably didn't hit that
There
one.
you go. You're in the share window now. Now click on the PowerPoint.
Now do
There
you
you
see
go.
that?
Yep.
Wonderful. Okay, very good. Well, I wanted to do a real short thing tonight. Basically, several of the people were interested in how do you get back and forth between noise figure and noise temperature. And then I got that little note down there, can a high noise figure burn my fingers? And I wasn't real sure of that. So I had to write this little series of things to see if it was going to burn my little fingers. Now, first one we'll talk about is amateur radio and radio astronomy use different measures for basically the same thing. And that is radio generally uses or measures receiver noise contribution in decibels. And the typical one for us and our little preamps that we build, uncooled preamps, are about 0.4 dB. Do a little better than that occasionally, but 0.4 is a pretty normal temperature for our noise figure for our preamps. And that's pretty much across all the frequency. We go from about 400 megahertz at the lower end, and then we go up to about 2 gigahertz, a little under that. And most all of our noise temperatures or noise figures come out to be around half a dB or less. And radio astronomers use temperature in degrees Kelvin, and a typical number would be around 25 degrees Kelvin temperature. And basically that's a load resistor or a resistor that puts out at the same amount of noise as your receiver at about 25 degrees Kelvin. Now, I understand 25 degrees Kelvin is a little colder than I'm used to, even though I'm from Minnesota, but it'd be make for some awful good ice fishing. Okay, and the reference temperature that you use for most of this, the reference is 290 degrees Kelvin, which is a little over 60 degrees room temperature or Fahrenheit. And so that's the reference. Now we'll go on into calculations. First of all, I'll define it a little bit. The system noise figure is measured at the antenna connections or preamp input. It's the noise contributions from the amplifiers, coax connectors, filters, etc. And remember last time the cascade noise equation works into that, because you have to pretty much figure out all of your gains and all of the losses in your whole receiving system to come up with a final number. System noise temperature is the temperature of a terminating resistance that produces the same noise as the receiving system. For measurements, noise figure stated in dBs, which is a logarithmic function. So for our equipment, it's normally less than 1 dB, as I stated. The noise temperature is stated in degrees Kelvin. 0 degrees Kelvin is absolute zero, and the lowest temperature theoretically possible. So now we've got a starting place for doing our figuring. Noise temperature is equal to 290 times the noise factor minus 1. And remember that you get noise figure is in dB, so it's a logarithmic scale, and noise factor is just converting that to a linear scale. And then we can do the mathematics after that. So then you get from noise figure to noise factor by taking 10 and raising it to the noise figure divided by 10 number. Example, find the noise figure 3 dB, noise factor 3 dB. Let's consider a 3 dB noise figure. So noise factor is equal to 10 raised to the 3 divided by 10, which turns out to be 2. So an increase in 3 dB is a factor of 2, and you often hear that, or a decrease of minus 3 dB is a factor of 1/2. That's where that comes from. The noise temperature is 290 degrees times the noise factor minus 1, which in this case, at 3 dB noise figure turns out to be 290 degrees, our reference temperature. So noise temperature, noise figure conversion. Up on top, you can see noise figure is equal to 10 times the log of the noise factor, and notice that I change noise factor is capital letters and noise figure are small letters. So that's when you see that in the literature, that's what they're talking about. Noise factor is capital letters. So you have to get it to noise figure to noise factor. And then the noise temperature divided by 290 plus 1 is the noise factor. So now take an example, you can convert 35-degree noise temperature, which would be a very good preamp, and to noise figure in dB. So you take the noise figure, 35 divided by 290 to get noise factor, 35 or noise temperature divided by 290 plus 1 gives you 1.12. And then the noise figure, the little ones, is equal to 10 times the log of the noise factor, which in this case comes out to be right under a 0.5 dB. It's just barely under that, 0.492 or something like that I computed. So that's the mathematics. Now we'll make it simpler. Noise figure is a figure of merit of receivability. Yeah, and then noise factor. Noise factor is a noise figure in dB converted to a linear equivalent. And the two of the most common ones are 3 dB is equal to a noise figure of 2 up, or noise factor of 2 up, 2 down. And then 10 dB, you would have a noise factor of 10. The noise temperature, the temperature in degrees Kelvin of the terminating resistor that produces the same noise as the electronics that you're using, LNAs, things like that. So now I went ahead and worked it out for you for various common noise figures, 0.1, 0.2, 3, 4, 5, up to 1, 2, 3, and 5 dB. Those would be all range. 5 dB is something that would be typical for a SDR, something like that would be running up in the 5 dB range. But our preamps that are much better than that go all the way down to, in our case, about 0.3 to 0.4 dB. So you can see on the right, the noise factor equivalent is in the noise temperature on the right-hand side. So we very often have a noise temperature of around 30 degrees or so, somewhere in there, 30, 35 degrees. Now, that, of course, suffers loss because added temperature, because of any relays that you have, any coaxial cables that you have, any connectors that you have. So that's why we tend to mount these things right at the feet if we can help it, or with a very short piece of low loss coax between them if we can. But so that gives you some sort of an idea of the numbers. Now we'll go from there. If you look at any of these, and I think we can put them on the website, but there's 4 different places where you can go with your computer and just type in the numbers, and it does all the calculations for you, and it doesn't make half the mistakes I make. So that's very good. And then this is a graph of what noise figure to noise temperature. So you can look it up. It's very easy. It's not real accurate when you get down below 1 dB, but you can guesstimate. It's pretty good. And I believe that's pretty much it. So that's all for tonight.
Any questions for Ray? A lot of
Ray, I
knowns
don't
and
remember.
unknowns
Do
about
we-
preamps, and what's the best one to use frequency wise you're operating, or so gives you a better understanding of when you see the numbers, what they all mean. 'Cause
Do
there's a
we
lot
have
of-
any estimate of what our system temperature is, the overall system?
The only time we've ever actually measured it, we came out with it seems to me it was between 150 and 200 degrees, and that was done at 400 megahertz, I believe. And that one, Rich Russell and I did a long time ago. But that was the only one that we've ever actually tried to study and do. We seem to not get down there enough to take some time and actually just sit back and calculate that and look at it. I suspect we're running generally right now between 50 and 100 degrees.